All right, so here we go with going through this worksheet. Certainly not going to read it for you. This is something that you were supposed to um, figure out on your own through reading, doing some due diligence, and I know a majority of you are. And this is really for a check to see what's going on here. All right, so this is actually historically accurate. The census, the amount of people in the United States at the time of 1790, and then Congress coming together in 1792 to figure out how many House of Representatives we should have and how many each state gets. So this was the actual process of trying the Hamilton method first. So what we first had to do is figure out how many representatives should we have. So the founding fathers decided that one representative should be for every 30,000 people. So the amount of representatives we should have is, it's nice, dividing the population by 30,000. And that's how many representatives we should start with. So check that out. And then reading those directions, rounded down. You're going to hear that rounded down quite a bit. A lot of these methods round down, lop off the decimal, and just deal with the whole number part. But that's how they first tried to calculate the Hamilton method using a base number of 120 representatives spread out among the first 13 states. Right? And then they talk about the state quota. Again, I wasn't going to read about all of this. And then this is just a reiteration of what we did with the Hamilton method. And if this is too confusing, just do what we did in the math. So, what is the value for D? All right, and then really we need to know what that represents. Boom. 361,005, blah, 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 divided by that, we get a number of 30,132.6. So when we lopped off that decimal and then redivided by 120, we didn't quite get that $30,000 or 30,000 people per one representative number. That's why that changed a little bit. But this is what we should have used. And if you didn't, stop this video and go to the next page and use that as your standard divisor to calculate, the state quotas. All right, now pause there for a second to just recollect. Okay, taking that standard divisor to the next page, and I actually should show you this. Remember doing the list feature? I know not everyone has a graphing calculator, but you can put all of these numbers in list 1, if you can recall how to do that. And then you can go to list 2 and then put at the very top of list 2 just L1 divided by, and then you could divide it by that 30,132.6. May show that later, but for right now, you should have already gotten this done, and we'll maybe do that when I show the Lowndes method. All right, boom. So here's what we should have got for our state quotas. And then, as always with the Hamilton method, they basically lop off the decimal part. That's called rounding down no matter what. So this is what we should have got for the state quota rounded down, which leaves a state quota of only 111, which means we have to assign 9 more seats. So that's something we should have read down here and understood about. When we lop that fractional part down, then this is what occurs. Okay, and then this is what I did. This is why you see these crossouts here. What I did, and it's kind of, tough on the eyes, but you kind of got to go through the fractional parts and see which one is the highest. And it looks like New Jersey has the highest fractional part. So what I did is I numbered that as, okay, 1. That's the first one to get an extra seat. Then 0.926, Virginia is the second one. And then the third one, 0.860, is Connecticut. So on and so on and so forth until we assign 1, 2, 3, 4, 5, 6, 7, 8, 9 seats based off of the largest fractional parts. So there you go. There's the new final tally of who gets the leftover representatives. And this is what was calculated in the first trial of finding out how many representatives each state should have. Okay, and then part two, this is new, but nothing that we've seen before, but it's easy. This is just what happened historically. Now what the founding fathers decided is, what's the state's average constituency? Here's the simple formula for that. So what you should have done is gone through and calculated what would the average state constituency be. So basically what you do is take this total amount of people divided by this 21, and that's where we get that 30,027. So that means each representative for Virginia they would represent 30,027 people. Okay, so you go along and keep doing that. So take the number of representatives divided by how many representatives there are, and this is what we see at the average state constituencies for each one. And this was a problem. And this is exactly what George Washington did not want to have happen. Did not want to have over-representation. This is really good. And again, hopefully you understand why this is. There we go. That's like the biggest, or actually the smallest amount of people, which means the best representation. Think about it. One representative represents 27,000 people, as opposed to Georgia, where one representative represents 35,418 people. That's bad. That's one representative representing more people's ideas, and then that one representative will vote on about those 35,000 people. So that's a worse representation. So this is why, truthfully, this is what occurred. What Washington did, in fact, veto this case, not about the underrepresentation, but it was about the overrepresentation. He did not want anyone having one representative representing better than 30,000 people. So this was actually vetoed. All right. So going through the next page, kind of gave this away using this method, which state had the best representation. So flipping to the third page, let's examine some issues of unfairness that resulted in this Hamilton's allocation. We just said that the state that had the best representation was Delaware, because one representative for 27,000 and change. Boom, which we just said. And then which one had the worst, which we just said was Georgia, because they had one representative for 35,000. Okay, and then all we have to do is read this and recalculate this if you got these wrong initially, what the absolute unfairness would be between these ranges. And that comes from subtracting the difference between the biggest to the smallest, the overrepresentation. And then what is the relative unfairness? All I got to do is read this right here, this simple little equation, to figure out how to do that one. So I'll give you a chance to calculate that. And we should have gotten, boom, 0.2754. And I think the founding fathers used that to try to see what was happening between the states. But you'll see as we find out what they actually adopted, it still ended up being a little bit unfair for some smaller states. We'll talk about that later. So hopefully you got all of that correct. That'd be awesome. And then this little thing right here, and actually this is true even though I wrote this back in the past. Monday, we are going to hit the Jefferson method. All right, but anyway, 10 days after Hamilton's method was rejected, Congress passed a new method of apportionment, now known as the Jefferson's method, in honor of, yes, that actual Thomas Jefferson. So we'll do that Monday. You excited? I know I am. Okay, so the rest of this, I was up and down about what was I going to teach the Lowndes method, and it was never, ever, ever used, but it was brought up. So I am going to go over it because it's really not a big deal. And I'll ask you one more question in order to see if you're paying attention. So you will be responsible for knowing a Lowndes method. He does do something a little strange, and I'm going to tell you what this method actually, who it benefits. By the way, Lowndes was from South Carolina, which was relatively a smaller state compared to some of the other ones. And he thought not just who has the biggest fractional part. We should test what is that fractional part relative to what you've already been given. So this is what he did. He still did the same thing, and you'll find many of these apportionments. They do their divide by the standard divisor, and then they round down, basically lop off the decimal. Some are different, and you do end up having 111 as what's given out. And then we have to figure out what to do with the extra 9. And then this is what he did. Not just the fractional part. He took the what's called relative fractional part. Can everyone say relative fractional parts? And it's the fractional part relative to what's already been given out as a amount of representatives. So I wanted to finish writing this down. So what you do is you take this 0.926 and you divide it by 20. And then you calculate that, and it's going to be a very, very, very small decimal. And you probably want to write that out to 4 decimal places. So there you get 0.0463. Then you take main, and you take, I put 15 first. Take 0.774 and divide that by the 15. I erase that little squiggle there. It looks like a 1 now. 0.774. Oh, that looks great. Well, you have to listen. Okay, so you heard me say, take that 0.774 and double back and divide it by the whole number 15. And you should get, come on, you said, all right, 0.056. 0.366 divided by 14, 0.732 divided by 11, all the way down the line, and calculate these relative fractional parts. And then lo and behold, when you start comparing who has the highest relative fractional part, now we got to know your little decimals. 0.843 is certainly much larger than anything that's 0.0 something. All right, so that's the first highest relative fractional part. Remember, we still have to give away 9 seats. Second largest one is 0.41. Third largest one is 0.198, and so on and so on and so forth. You got to be really careful, especially since there's so many seats to give out of who's the largest and the next largest. So we had 5. 6.1407 is slightly larger than 0.14. Certainly slightly larger than 0.136. This is why you have to take it out to like 4 decimal places to get these comparisons. And then something you should know about Lowndes' method is, where's Lowndes from? He's from a smaller state. And who ended up getting all of the extra delegates off of his method? All of the smaller states ended up with the extra delegate according to his calculations. So this was actually brought up. Historically, it was tried, and it was vetoed immediately. And I don't know if it was ever brought up again, but never, ever used as a way of apportioning. So those poor small states. Anyway, you will be responsible for that because it's really not a big deal. It's just a process. It's a very easy process, and it's just something that has to be memorized and just requires you to actually watch a video and do the work. And blah, blah, blah. Oh, here I go. Now I'm getting on my little high horse. All right, so I'll cut it off there and leave you alone. Have a good day.